Hey guys, let's talk about the medicinal chemistry of central analgesics. As you go through the notes, these are the reading objectives that you will be responsible for. Basically, make sure you study the structure of the endogenous opioid peptides and their structure-activity relationship, and see the similarity between these endogenous opioids and the morphine. Okay, and then relate the structure similarity of the opioids to the receptor selectivity and how this can affect the cross tolerance. So basically, how similar drugs can bind to the same receptor, and how can these similar drugs also can have cross tolerance, which is important in the case of opioids withdrawal, and also important in the case of opioid rotation concept, where a patient is in chronic pain, or a cancerous patient will take these opioids for a long time and then will have to rotate them so we don't get to the tolerance. Then identify the pharmacophore, which are the structural features important for the activity of these morphines or these opioid peptides, endogenous opioid peptides. And then explain why did we come up with these prodrugs such as codeine instead of using the morphine. And then pay attention to the inter-individual variation in some metabolic enzymes and how this can affect toxicity, because as you will see, codeine, for example, is a prodrug, and then it needs an enzyme to be activated. So pay attention to how these activating enzymes could, be overexpressed or underexpressed, and how this can affect the toxicity or the efficacy or the activity of these prodrugs. And then also study the structure-activity relationship for the opioid agonist antagonist and identify the structural feature, which is actually the one attached to the nitrogen. Identify that feature that's responsible for making an opioid drug as an agonist, a partial agonist, or even an antagonist. And then explain why do we combine some of the opioid antagonists, such as naltrexone, naloxone, with other opioids, such as morphine, for example, as in the case of the Embeda. And then list examples of opioids designed with lower analgesic activity, yet they have better pharmacokinetic properties. In other words, in this objective, you will see examples where we compromise the activity for the sake of having better pharmacokinetic properties, and overall we have a more active drug. Okay, and then identify the advantages of using the mu agonists, such as buprenorphine, over the full agonist, and then the advantages of using the kappa agonist, the mixed kappa agonist, mu antagonist over the full mu agonist, and why is naltrexone can be taken orally while naloxone cannot. Finally, explain the rationale behind the design of methyl naltrexone. Why did we add the methyl to the naltrexone, such that it could be used only for treating constipation. Okay. There's few other concepts that are only tested here, which is basically related to the use of methadone, why it has long duration of action, and also in the case of the use of the opioids for treating diarrhea. Okay, like the loperamide and the diphenxylate. Okay, and as you go through the notes and the voice over notes, you'll see that these areas in gray are, you could skip and just read on your own, because some of them are clinical or pharmacology, so you could read them on your own. Let's start by the list of drugs covered and we will talk about today. There is the analgesics, classified as the full agonists, full mu agonists, partial mu agonists, and the kappa agonists and mu antagonists. So these ones here work as an agonist on kappa but antagonists on mu. And then we have the opioid antagonists, and then we'll also talk about the full mu agonists, and we'll talk about those that have dual action analgesics. We'll also talk about some of the drugs that have similar structures to the opioid drugs, but they work as anti-diarrheas. And then these are for your own reading. You can find that in the chapter posted on Blackboard, as well as these. The same applies to the ones that are in gray area, so you could read them on your own. This is for your own information. I should point out that I really don't care about this particular class, whether it's a multi-cyclic or flexible or not. But I do want you to know which ones are full mu agonists and which ones are partial and on each receptor. Okay. So to start with, there are the opioids that are endogenous peptides. Basically, these are proteins that are synthesized by our bodies. Obviously, otherwise we would not have receptors for. Although in fact the opioid drugs like morphine and its derivatives were used way before the discovery of the endogenous opioid peptides. So the drugs were known before knowing that there's actually peptides, but they expected, since there's receptors for the opioid, that there must be something endogenous. So these endogenous peptides, normally they are derived from large proteins, precursors, and then these proteins are divided, basically cut, by enzymes called proteases to produce the specific opioid peptides. Okay, so, and I want you to know basically that, you know, these are examples of the opioid peptides. For example, the proenkephalin A is the precursor for the meth and enkephalin, which we'll visit in the next page. And then proenkephalin B, a precursor for the dynorphin and the alpha neodynorphin. But really do not worry about memorizing any of these. Just, get the general idea that there are actually endogenous peptides, and we will look at comparison in structure between the endogenous peptides and the endogenous peptides opioids and the synthetic opioids, drugs like that. Let's see the next page. So this here shows the steps of the synthesis of these endogenous peptides. So they are synthesized in the nucleus, and then they are transported, processed through proteases, as we explained earlier, and then now these endogenous peptides are released. They bind to the receptor and produce the effects, the signal transduction effect that I'm sure you have learned in pharmacology. And of course, the NX here are an example of the antagonists that block the receptor, and then the OP are example of the synthetic opioids, the drugs that bind similarly to the endogenous peptides. They bind similar to the natural endogenous opioids, and they produce the same effect, the analgesic effect. Okay, so here is the list of the endogenous opioids, which is basically polypeptides. Polypeptides are made up of amino acids. So in this example, we have 5 amino acids, 5. Here we have 31, and so forth. So notice that all of them, or almost all of them except this one here, the nociceptin, they start with tyrosine, glycine, phenylalanine, and then they either have a metformin or a leucine. Metformin, and this is an exception. Oh, actually, this is part of that. Never mind. And then leucine. So all of them starts with the tyrosine, glycine, phenylalanine, and then they either end up with metformin or leucine. Okay. So we will see that these parts, amino acids, matches the synthetic opioids, the drugs. Let's talk about the structure-activity relationship for these endogenous opioid peptides. All these endogenous opioid peptides, like we have seen in the previous page, have the starts with the 5 amino acids, tyrosine, glycine, phenylalanine, and end up with either, they will have at the fifth position either L-leucine or metformin. There is an exception to that, which is the endomorphin. So the endomorphin starts with tyrosine just like all the others, but then it has proline, amino acid, tryptophan and phenylalanine. So all the endogenous opioid peptides, or majority of them, except this one, have the what's called starts with the new met enkephalin. New met enkephalin, which would be this part. So all of them will um, have tyrosine at the first as the first amino acid. In fact, this is important, as number 2 says, the tyrosine amino acid is one of the essential amino acids for activity. No wonder why it's present in all of them, not just the, all of them including the endomorphin. So even though endomorphin has different amino acids, but it also starts with the tyrosine. So tyrosine is the most essential one because of the two major function groups, as we'll explain further. The hydroxyphenyl, this phenyl group with the hydroxy OH, okay, plus the nitrogen here. Before we move forward, let me briefly remind you of how these amino acids are named. If you remember, peptides or polypeptides, proteins basically, are a chain of amino acids. These amino acids are linked through the what's called amide bond or peptide bond, which is right here between the carbonyl and the nitrogen. And this function group is the one that helps you decide what type of amino acid is. So in this case, it would be tyrosine. In this case, there is a hydrogen here, so it would be glycine. And then again, there is the C double bond O nitrogen, so that's an amide bond. And then you have glycine, and then again another amide bond that connects the two amino acids together. And then you have this function group here, defines the phenylalanine amino acid, and then you have again the amide bond that connects each amide. Here the amide bond that connects the two amino acids. So the last one would be the leucine. The same applies to here, except the last one here is metformin, and then of course the same applies here, but has different amino acids. Okay, so like we said, the most important ones are actually the amino acid tyrosine, because of the phenolic OH group and the phenyl group, as well as the nitrogen. So this explains what this sentence here says. Number 2, tyrosine, the first amino acid, is the most essential, and the removal of the hydroxyl group or the phenolic hydroxyl group, or removal of the basic nitrogen here, would cause abolish or loss of the activity. Okay, and then we will talk about the substitution on the nitrogen. Basically, if it's alkylated, then it can affect whether this drug is an agonist or antagonist. Okay, so in addition of the phenolic and amine group, the next most important moiety is the phenyl group of the phenylalanine here. So after these two groups, the OH with the phenol and the amide here, the the basic amino nitrogen. The next most important is the phenylalanine here, which is present here and here. Okay, and we will see it as part of the structure of the morphine. But anyway, this is the next most essential. So removal of this group or changing the distance between the tyrosine and the phenylalanine would cause loss of the activity. Okay. Okay, the next relationship that relates structure to the activity is the fact that these enkephalins have many low energy conformations, which means, well, first let me remind you, a conformation is any difference in the structure that results from rotation around a single bond. So as you can imagine, anytime you rotate any of these single bonds, you will have a different conformation. Basically, these groups will be aligned or positioned in different locations in space. So because of that, because they have different conformations, then they are able to bind to different opioid receptors. As you know, there are 3 or 4 opioid receptors, and changes in these conformations allow these drugs to bind to these receptors. You will notice that the synthetic drugs, were actually more strained, so they don't have much options to rotate. So then we could actually design them in a way to fit one receptor but not the other. Okay. The next sentence talks about um, the amino acids and the chiral center in the amino acids. So all these amino acids will have a chiral center, well, except for those that have hydrogen, like glycine. So as you will see, this is a chiral center here. This is a chiral center here, same as this one here. So anytime you have chiral center, it means you can have R or S. In the case of the amino acids, we call them L and D. Okay, so it's just a different way of referring to the isomers, due to the having a chiral atom. So naturally, our body synthesizes the amino acids in the L form, in the L isoform. If we synthesize these molecules and use the D amino acids, then our body will not be able to metabolize these, because our body is designed to metabolize the natural amino acids, which are in the L form. So if we replace them by the by the D unnatural amino acids, then these peptides could be resistant to the degradation and metabolism. Why is this important? Well, if I synthesize this molecule and substitute all these natural amino acids with the D amino acid instead of the L, then these molecules can stay longer in our body, and then they can cause the analgesic effect that we're looking for. Okay, the only thing is, and this is, by the way, is a technique that we will see a lot later on, whenever we have part of a protein that we need to stabilize it, then we could replace the natural amino acids with unnatural simply by converting the center, the chiral center, from L to D, uh, or which is an example of our R and S, is the one you are familiar with. So anyway, converting L to D, then these become resistant against the the body. The only problem is sometimes these proteins can become not they can lose their activity, because the position of these molecules, of these groups in space, would change. Okay, so that's one way of increasing, basically synthesizing something and increasing its stability. And then another way also to stabilize these molecules would be changing the terminal carboxyl group, which is right here. Terminal means at the end, carboxyl group here. Changing it into alcohol, so instead of COOH, just keep it OH, and then this would protect the group here from the carboxypeptidase enzyme that breaks this amino acid. Okay. And then finally, the introduction of the D or L amino acid again would cause increase in would affect the affinity. So basically, although we can make it more stable, but then it can affect the affinity of how these peptides, the endogenous peptides bind to their receptor. Okay, and then, like I said in earlier, So if we are able to, so the synthetic drugs are actually more strict. They have less ability to rotate, so they can bind different. Sorry, they can be selective to opioid receptors, while these are more flexible, so they can bind to many opioid receptors. This is in sentence number 8, which you cannot see here, but you can read. Okay, so this concludes this part, the structure activity relationship. I do want to talk about how the morphine actually matches with the one of these peptides, which is the metenkephalin. So this is the structure of the metenkephalin. Again, this is the tyrosine, glycine, phenylalanine, and the metformin. And this is the morphine. And if you try to look for the common feature in these two, you can see that the phenolic OH here, the phenyl group, along with the nitrogen here, these are the ones that are essential for the activity. They match. Of course, the next essential will be this group here, the aromatic group here, which matches this group here. Okay, so you will see that this link, the nitrogen along with the phenyl with the phenolic OH and the phenyl group, are the most essential for the activity. Okay, and of course you see that here you have CH3, but here you have hydrogen, and we will see how this affects the activity. And then when we talk about structure activity relationship for the synthetic opioids. Okay. The next thing I want to talk about is the analogy of the message address concepts. So basically, because there are many kinds of opioid receptors, and we need to design drugs that can target some of these receptors but not the others. And we also would like to design drugs that work as an agonist or a partial agonist or antagonist to each one of these receptors. This analogy or this concept became useful because it helped us understand which part of the structure is responsible for binding to the receptor. Basically, which part of the structure is responsible for selecting the opioid receptor, and which part is responsible for deciding whether this should be an agonist or antagonist or partial. Okay, so in this example, um, this part here of the um, synthetic molecule is responsible for delivering the message, which means that the message could be an agonist or antagonist. Notice that the nitrogen here is part of that message, and the group here attached can impact whether this drug can be an agonist or a partial agonist or even an antagonist. Okay, so this will be the message that will be delivered once the drug binds to the receptor. Okay, now which part of the drug will help us um, decide what receptor that drug should bind to? It's actually this part here to the right side. So this part, this function group, the change in this function group will help us decide whether the drug should bind to the mu, the delta, or the kappa. Here's another example here. The right side will direct the molecule to the type of receptor it wants to bind to, whether it's a mu receptor, a delta, or a kappa. And then the left side decides whether the drug should be an agonist, antagonist, or a partial agonist. Okay, so here are some examples. Naltrexone, NTI, and NOR-BNI. I'm not sure what these acronyms are, but don't worry about them. I'm just trying to explain the concept here. So in the case of the mu receptor, this was the part that's responsible for selecting the receptor, and the same applies to the delta and the kappa. Okay. In fact, this also applies to the peptides, the opioid peptides. So the first amino acid, which has the tyrosine with the nitrogen, would deliver the message, but then the remaining of the amino acids, the 4 amino acids, would affect where this molecule should bind to. However, in the case of the endogenous peptides, they were actually binding to all the receptors because, like we explained, they are more flexible, so they can bind to more receptors, while these drugs are less flexible, so they are more selective to the opioid receptors. Okay, next is the cross tolerance. The cross tolerance simple idea is very simple. If two molecules are similar, then they should have um, similar ability to produce tolerance. So if I'm given a drug and the patient becomes tolerant to this drug, then if I want to switch it to something else, if it's within the same, if it's similar to that drug, then I will not have any withdrawal symptoms. Okay, so the concept of the cross tolerance would help us avoid the withdrawal symptoms. Okay, so you could switch from one drug to another and be certain that the patient is not gonna get these withdrawal symptoms. Normally, these drugs have similarity in their structures, and they have similar pharmacological activity. So they are either agonists, for example, to the same receptor with similar structures, or they are partial agonists. But we cannot switch, for example, from agonist to a partial agonist without expecting to have withdrawal symptoms. Okay, normally, if somebody is taking an opioid for a long time, then we switch from one to another to, make sure that that person does not get used um, to one drug. So we alternate from one drug to another within the class of drugs that have cross tolerance. Okay. Let's now talk about the opioid receptors. As you know, there are 4 types of receptors. I just want you to pay attention to few things here. Basically, the effect of these receptors upon activation. All of these would produce analgesia. The mu receptor would cause euphoria, but the GABA receptor would cause dysphoria, which is the opposite of euphoria. The delta, actually, I was looking at some of the pharmacological books. They say that it can also cause dysphoria. And the reason for stopping the synthesis of opioids that bind to this receptor is because it can cause convulsion. So far, the ones that have been targeted are the mu receptor for the analgesic effects. Okay, because targeting the GABA or the delta would give us some problems. And of course, all of them cause the respiratory depression, which is the major cause of the death for the opioid overdose. This one here affects the volume of the respiratory center, the amount of air you actually inhale. This one affects the rate of the respiration. Okay, so just basically focusing on the major pharmacological effects, and the rest is just for your own information. As far as the physiological and metabolic properties of opioids, in particular the lipophilicity, the association constant, which talks about this nitrogen here, how it's going to be ionized or unionized, and the pharmacokinetic properties, the major points I want you to pay attention to is the fact that these drugs should cross the blood-brain barrier, and to do that they should be lipophilic. Now this nitrogen here can be ionized, and so when it's ionized it won't be able to cross the blood-brain barrier, but since there is an equilibrium between the ionized and unionized form, this drug can cross the blood-brain barrier when it is in the unionized form. Okay, and then the stereochemistry I hope you still remember the example of the roboticin, the dextromethorphan, and the levomethorphan, or the codeine. I think we talked about the codeine, how it binds to both the cough center as well as the opioid receptors, while the dextromethorphan binds only to the cough center but not the opioid receptors. So basically the opioid receptors prefers the levo form, okay, the levo isomer, which are naturally synthesized. And also when we design drugs, we want to make sure they are levo if we are trying to target the opioid receptors. Both levo and dextro will be able to bind to the cough center and cause, stop the cough. That's why these drugs like codeine can also be used as antitussive. But if you wanna get something that would stop the cough but not bind to the opioid receptors, then we'll go with the dextromethorphan, which is why it's available over the counter. So hopefully you still remember the example and the demonstration we did in class with the glove. Okay. This table here summarizes all these physicochemical properties, such as the lipophilicity. So log D is another name for log P, the partition coefficient, or also referred to as log K, oil in water, which gives you lipophilicity. Basically, the ratio of how the drug results in oil compared to how much it dissolves in water. So the higher the number, it means more lipophilic. So as you increase the number in this column, then the drugs are able to cross the blood-brain barrier, which is good in designing drugs. And then also talks about the bioavailability, the binding affinity, the binding to the proteins in the plasma, the volume distribution, the half-life, duration of analgesia. Most of them have short durations. They would be administered frequently. And then excretion would help us to decide if somebody has kidney problems, then we would avoid those drugs that are excreted by the kidney, renal. But if their liver, if the problem is in their livers, they have liver problems, then we'd look for drugs that are excreted in the kidney. Okay. We will, I'm sure you will learn about this more. The maximum duration of action, or no, the time it takes for the drug to give you the analgesia. Some of them are shorter than others, 30 minutes compared to an hour or two. This one is 15 minutes. This one is, of course, IV is an exception. IV 8 minutes. And then the onset of the analgesia. So this is when the analgesia starts. This is when the analgesia gets to its maximum. Okay. So really, this is just for your own information. Just make sure that if you have the higher log partition coefficient, then it's more lipophilic. It will cross the blood-brain barrier more. Okay. Let's now talk about the metabolic reactions for the opioid drugs. Before I do that, let me remind you again, this is the example of the morphine, I believe. Yes, it's the morphine. So let me remind you that the highlighted area, or the parts in red, are the essential for the activity. So the OH group here should be cleared to be able to form hydrogen bond interaction. And the nitrogen here is also essential. It could have a CH3, which is preferred. So any changes to this part or this part will affect the activity. And in fact, any changes to this nitrogen here can also affect the type of action this drug can produce. It could be agonist or antagonist. And then the rest of the molecule would affect the lipophilicity, how lipid soluble the molecule is, and if so, it will be able to cross the blood-brain barrier. So anyway, the common metabolic reactions. There are two common reactions that occurs as far as phase 1 metabolism. Remember that in metabolism has two phases, phase 1 and phase 2. So in phase 1 there are two common reactions, and then in phase 2 there are another two common reactions that happens to these drugs. So let's start with those that occur during phase 1. There are two kinds, and both has to do with the demethylation or dealkylation. First, on this OH group here at the position 3, the O group here at position 3, and this is known as demethylation, and the second at the nitrogen, which is called N demethylation. So you have O demethylation and N demethylation. So if we start by let's talk about the N demethylation first. Okay, so in this example, the N demethylation for any of these drugs, okay, and for the morphine, for example, which is here, if you remove the methyl group from the morphine, the demethylation, the resulting product is gonna be less active. First, because it is less lipophilic now. Remember, CH3 compared to the hydrogen, the CH3 increases the lipophilicity. So by removing that CH3, the drug is now less lipophilic. It's less able to cross the blood-brain barrier. Second, the CH3 here apparently has some binding lipophilic site at the receptor, so removing it will also decrease its binding affinity. So anytime we remove this part will result into less active molecule. Okay. The second example of the phase 1 metabolism is the O demethylation, and in this case we actually produce a more active molecule. In fact, morphine has no methyl group attached to it, but if we do attach a methyl group or any alkyl group to the OH group here at position 3, then we end up having something like codeine, which is inactive. That's why codeine, for example, is not as a prodrug, because it is not active. We will see why codeine was designed in the first place. Well, let me give you the answer now. It's basically to enhance its stability. So the OH group here could be used to further metabolized into the sulfates. So the short answer is to protect this OH group from being metabolized into the sulfates, we designed this morphine. We added CH3 here to protect it. So then the drug, when it's absorbed, it goes through the liver, it's activated to the morphine, and then it goes to the blood-brain barrier, and then later on, after it binds and produces the effect, it goes back to the liver, and at second round, it gets metabolized and excreted. Anyway, so back to the phase 1. Second type of phase 1 reaction is the O demethylation or O dealkylation, like the example of the codeine, and in this case the molecule is converted into the active form. The enzyme responsible for each of these two cases are the CYP3A4 in the case of the N demethylation, and the CYP2D6 in the case of the O demethylation. This enzyme here varies from one person to another, unlike this one. So people who have problems with this enzyme, whether they have less of this enzyme or more, let's say most likely people who have less of this enzyme is most likely to happen. In this case, people who have less of this enzyme, then they will not be able to convert the codeine into the morphine, and they will not have the analgesic effects. Okay. I also want to mention that there's a drug called heroin. In the case of the heroin, instead of the CH3, we have an ester group here. So an ester is attached here as well as here. So the first stage is a hydrolysis of the ester, which causes the drug to be activated. So this is inactive form, and this is active. Okay. So the first stage is removing of the ester through the process called hydrolysis. So, and in fact, hydrolysis is considered part of phase 1, so that could be a third example of phase 1 metabolism, which is the hydrolysis of the heroine. So then you get this molecule, which is the 6-monoacetyl morphine, and then it's further hydrolyzed into the morphine, which is active. Both of these are active, but this one has better pharmacokinetic properties because it's able to cross the blood-brain barrier, unlike this. Okay. Anyway, so we have 2 or 3 examples on phase 1. On phase 2 metabolism, there we have 2 examples. One is the sulfation, and it would produce inactive form at if a sulfate group is attached to this OH at position 3, which is the reason why we added CH3 here to protect this OH, such that we do not lead to such that the molecule does not go into this step of phase 2 metabolism, but eventually it will. Okay, but just to buy some time such that the molecule stays longer in the body, we added CH3, so now the OH is protected, and now the drug stays longer in the body before it's converted to the morphine, the active form, and then it's able to produce activity, then it's metabolized. Besides, the addition of CH3 here also improves its pharmacokinetic properties. The drug is more lipophilic, it's able to cross the blood-brain barrier. Okay, now this is all about the first stage of the first example of the phase 2 metabolism. Second example of phase 2 metabolism is the glucuronidation at this position here, the OH at position 6, not 3. Okay, so we have conjugation at 3, conjugation at 6. This by sulfate, this one is by gluconate. So what's unique about this second example of phase 2 metabolism is that the resulting product is actually more active. So this was surprising, which is that the addition of this glucuronate has resulted into something that's even more active than the original drug. Okay, so we have codeine inactive, we have morphine active, and then this product, the glucuronate form, is even more active. Okay, and so to summarize, phase 1 examples on phase 1 reactions are the O demethylation or O dealkylation, and then the N demethylation again, or N dealkylation, and hydrolysis. Phase 2 has 2 examples, or 2 positions actually, can be 2 positions where phase 2 can be performed. The first one is at position number 3, where morphine conjugation with sulfates, or actually glucuronide also, not just the sulfate. So conjugation at position OH3 here could be either with a sulfate or glucuronide, will give you an inactive form. And then the second position is the conjugation at position number 6 here, position number 6, which would surprisingly give you a more active form of the morphine. Let's now talk about the structure-activity relationship of the opioid agonist and antagonists, so the synthetic opioids basically. Starting with the multicyclic opioids. In fact, we will only talk about the SAR of the multicyclic because the others are very similar to the SAR of the multicyclic. So we'll start. This is the generic structure for these multicyclic. As you can see, we have 1, 2, 3, 4, and 5 cycles. So they are called the pentacyclic. Okay, morphine is an example of them, and we'll look at the substitutions at each of these R's: R1, 2, 3, and 4. So starting with R1, the most common substitution for the R1 is actually the methyl, as we see here in the morphine. However, as this graph shows here, if we increase the substitution, the size of the substitution at R1 from methyl to ethyl, so from 1 carbon to 2 carbons to propyl, which is 3 carbons, as we increase the size, the agonist activity decreases and the antagonism increases. and it reaches the maximum when we have the well, it reaches the maximum antagonism when we have propyl. Now, if we add a double bond, so this is a propylene. So this is propyl 1, 2, 3. If we add a double bond here, it's a propylene. Or if we make this as part of the cycle, as in the cyclopropylmethylene or the allyl group, if we add these groups, then the drug becomes completely antagonist, as the example of the naloxone, where we have the allyl here, or the naltrexone, where we have the cyclopropylmethylene. Okay, so naltrexone, trex, triangle, and then the allyl for the naloxone. So these are antagonists. What's interesting is if we continue to increase the size, we reach to the butyl, then the drug will have zero activity. It's not going to do anything, neither as agonist nor as antagonist. If we further increase the size, the length of this chain to pentyl or hexyl, it goes back to an agonist. Okay, so we'll have an agonist activity, and for example, if we further increase it to the phenyl, it's actually called the phenyl group, then we'll have the maximum activity. The activity of this drug with this substitution is actually 14 times more than the morphine, which is our reference. Okay, I also want to say that with the naloxone or the naltrexone, not only we substituted the R1 with these groups, but also we replaced the OH here. I'm sorry, here, the OH group here at position 6 with ketone, and at position 14 here we added an OH group. So as this sentence here says, 14 beta hydroxy and 7,8 dihydro. Oh, I forgot to say we removed the double bond here. Okay, which is here, 7,8 dihydro on. So we have dihydro, we have ketone, and we have an OH group. In addition to these two, were optimal for the antagonist activity. Okay, so I think that's all for the R1 substitution. I just want to say that the substitution, or these antagonists, the pure antagonists, have their highest affinity to the mu receptor, but at higher dosages they can actually block all the opioid receptors. The rest here talks about the selectivity at the GABA, at other receptors such as the GABA, and that some of these drugs could be, while they are antagonists at the mu, they can at higher dosages become agonists at the GABA, but it's not clear which structures are they referring to, so I'm going to skip this paragraph, and I'm also going to skip these two because they're not really important. Anyway, so that's all for the R1. Okay, let's now talk about the R2 substitution, which is this one here at the R2 at position number 3, which talks about the OH at position number 3, the phenolic OH, which is an essential part for the activity of the morphine. In fact, you should already know by now what's the the importance of the R2 substitutions and what happens. We have already talked about that in the metabolism, but let me quickly reiterate. So as you remember, the OH should be free, should not be bound to anything, so it could form hydrogen bond with the receptor. If you substitute it with anything like a methyl group, or if you conjugate it, or if you add, for example, the acetyl group, then the drug becomes inactive. So in the case of the methyl, we have the codeine, which is inactive, and then it's converted to the active form morphine. The problem is only 10% of the codeine is converted into the morphine through this enzyme, the O demethylation, which is the primary reason why codeine has a much less activity than morphine. But again, with the CH3, it increases the lipophilicity, so it's it can cross the blood-brain barrier. Plus, the codeine would stay longer in the body before it converts to the morphine, and then the morphine eventually is converted by this enzyme here to the inactive form by the sulfate. It's also converted to this inactive form by the N-demethylation or N-dealkylation enzyme. I also should remind you that this enzyme varies again from one person to another, which plays an important role, as we'll see in the example next page. So those who are poor metabolizers for this enzyme, those who have less amount of this enzyme, will not be able to convert the codeine into the morphine, and so you will need to increase the dosage of the codeine in order to get enough analgesic effect of the morphine. Now, if you do that, like in the example in the next page, if you do that, then you might have someone who's taking this medication, the codeine, and she is breastfeeding her baby, but the baby has normal amount of this enzyme. She has less amount of this enzyme, so you'll have to increase the codeine, and then the baby to get the analgesic effect, but then the baby has normal amount of this enzyme, so he's going to get more of the morphine, and that could cause respiratory depression, and which causes death. Okay, it's even worse if the baby has even an ultra rapid enzyme of this enzyme, ultra rapid metabolizing enzyme, then we'll have even more of the morphine. So that's one scenario. The other scenario, which is actually so there are two stories or two scenarios listed in the next page. The other scenario was that the mother had actually ultra fast metabolizer of this drug. Okay, so she ended up feeding her child who's actually a normal metabolizer for this enzyme. She ended up feeding her child morphine, but that was not the problem. The problem was that both of them, the mother and the child, had a rapid metabolizing enzyme that converts this morphine into a higher, more active form. Like if you remember, the metabolite here was more active than the morphine itself, so then that caused the death of the infant. Anyway, generally speaking, these enzymes should be taken into consideration, as they vary from one person to another. And then there are some numbers that shows, for example, that 7.7% of Caucasians are deficient of this enzyme, while the percentage in African American varies from 1.9 to 7.3%. Okay. The only thing left as far as the R2 substitution is the fact that that OH group, actually the phenol group, will go into oxidation to produce an inactive quinolones, and therefore so this is in vitro, meaning like if they're exposed to the oxygen in the air or to the light, so they should be avoided, should be protected from light or oxygen or any base chemicals to keep them active. The next group is the R3 here at this position, which is 14, position 14. So the addition of an OH group, adding OH group at this position, or basically using OH as the R3, if the R3 is equal OH instead of H, like in the morphine, if it's an OH group, the addition of OH group here would increase the activity and the ability of the drug to bind to the receptor. Okay, problem is the ability to cross the blood-brain barrier would be reduced, because now the drug is more polar, so it is less lipophilic. However, if we put these two together, if we compare which is which has better effect overall, then the binding affinity and the increase in the activity is significantly more than its effect on is stronger than the ability of the drug to cross the blood-brain barrier. So basically, the addition of OH would override the negative effect of not being able to cross the blood-brain barrier. So overall, by adding an OH group here or using OH for R3, we'll have a 2 to 3 increase in the opioid activity. Interestingly, that is not the case for the cough receptors. So adding an OH group here would decrease the anti-tussive effect for these opioids, and opioids who have OH group here are not used for that activity, not used as an anti-tussive. Okay, the last group you're going to talk about is the R4, and in the case of the R4, we cannot separate we cannot talk about R4 without talking about the double bond here at position 7 and 8. So anytime we talk about R4, we should also talk about double bond, and it's a little bit tricky, so we're gonna try to simplify it as much as we can. So first of all, there should be an OH group here, okay, for the drug to be active. If we remove the OH group here, then the binding to the receptor will be reduced. However, the drug becomes more lipophilic and it's able to cross the blood-brain barrier. So when you put these two together, compare the negative effect with the positive effect, the lipophilicity wins, and the drug becomes, overall, the drug becomes 10 times more active. So this is this point here. Removing the OH would reduce the activity, but the drug is more lipophilic. Overall, you get 10-fold increase. Okay, and this is just by removing the OH, and we have not changed anything with the double bond. Okay, the second thing is if we replace the OH group with a double bond O like this, okay, then the activity is reduced. So moving from this to that, only replacing the OH with a double bond O, but except we are not removing the double bond here between 7 and 8. So if we only replace the OH here with a double bond O, then activity decreases because the ability of the drug to bind to the receptor is reduced. Okay, but if we replace the OH group with a double bond O and remove the double bond here between 7 and 8, then the ring here becomes more flexible, and the double bond on O here, the ketone, with the flexibility of the ring, makes an increase in the ability of the drug to bind to the receptor, and this will have 6-fold gain in the activity overall. Okay, so basically three major concepts here. Finally, there's just a note about the fact that the presence of OH group here is responsible for the allergies. For people who have allergies to these drugs, you could try to look for other drugs that do not have the OH group at position 6. So this is just something to keep in mind. The SAR activity for the flexible opioids I'm going to skip because they are very similar to the ones we seen before. Okay, so now let's talk about specific examples of these opioids, and we'll start with the full mu agonists, the multi-cyclic full mu agonists. In fact, if we understood all the SAR properties and all the metabolism and the basic stuff we talked about, then the rest of these notes should be easy to follow. Okay, so starting with morphine, it has a very poor oral bioavailability due to the fact that it's highly polar, so it's does not cross the blood-brain barrier. Second, due to the fact that it's goes through extensive metabolism. When it goes through the first pass effects, it's metabolized by the liver. Mainly this position here, position number 3. If you remember, in the metabolism, it's conjugated with the sulfate or the glucuronide, so it would give you an inactive form. In fact, that's why we would design a codeine to protect this OH group. But anyway, so it has a very low bioavailability, and it has low. It has a low lipophilicity, so it's not able to cross the blood-brain barrier. And that's why actually when it's given by injection, we can bypass the liver, um, the first pass effect of the liver, and then the activity would be much higher if it's given intramuscularly than if it's given to orally. So it would be like 6 folds more active if it's given through the intramuscular route. Okay, and of course another um, way of being deactivated is by removing the methyl group here. So the N-dealkylation again is one of the things that makes it inactive. It reduces the activity to 20 times less active. And then interestingly, the metabolism on this part here, on the 6, like we said earlier, would make the drug more active, which is actually believed to be the reason why morphine even retains some activity. Okay, in fact, the phase 2 metabolism at this position number 6 here would produce the glucuronide conjugate of the morphine, which is 50 times more active. Okay, and then just disregard the rest of the stuff on this page. So morphine is actually available in many dosage forms: injection, oral solution, tablets, both immediate and controlled extended release tablets, as well as extended release capsules. Examples of the extended release capsules are Avenza and Kadian, although I believe Avenza has been discontinued. Those people who do not want to be reminded to take their pain medications, or if they take it for a long time, then it's better to give them these extended release tablets. Now, if they have, capsules, if they have problems with swallowing these capsules, then they can open the capsule and just, sprinkle it over on the food and swallow the food, and, they would still be, extended release, as long as they do not chew these sprinkles. Okay. Problem is that, well, before going to the problem of abuse, I should say that um, consuming alcohol with these opioid drugs, or with morphine, for example, is never advised, because it causes depression, and it can causes I guess make the respiratory depression even worse. But then another factor of alcohol would promote the rapid dissolution of these tablets or capsules in the stomach, so then you'll have more of the morphine. Okay, and then next we'll talk about the fact that the morphine sulfates, or these extended release tablets, could be abused, and therefore a way to avoid that is to add um, naltrexone to these extended release tablets. So these, capsules, they have the morphine in pellets, in a small oval like spheres. Inside these pellets, there is the extended release morphine, and then surrounding around these pellets, you have the naltrexone. So if somebody tried to abuse these drugs and crush the pellets or the capsule, or chew them to get the euphoric effect, then the antagonist naltrexone is released, and then it would block the effect of the morphine and would prevent the euphoria. So then it's just a way to prevent the abuse of these products. Okay. This figure is to help you visualize how the technology in Embeda works. I found this nice picture that would make things much simpler. So this is the capsule Embeda, and it has these pellets, spheres, and in the middle here of the pellets, these small pellets, in the middle there's the naltrexone, which is the antagonist. Okay, it works at the opioid receptor, and then there is a membrane that protects the release of this naloxone. So as long as this whole pellet is not crushed, the naltrexone stays inside this membrane. Okay, and outside you have the morphine sulfate, which is surrounded by this membrane that controls the release of the morphine. So if the capsule is taken normally, then morphine is released gradually over the day. It binds to the receptor. So this is the receptor, opioid receptor. It binds to the receptor. You get the analgesic effects, and these naltrexone is never released. Just leaves the body with the feces. Okay, outside the body. Now, if the patient crushes these pellets which comes inside the capsules, then this membrane is also broken. So besides the morphine, they will also get the antagonist. So both of these, the agonist and antagonist, will compete at the receptor. And of course, the naltrexone has a stronger binding affinity to the receptor. That's why it's actually used to treat people who take morphine or overdose on morphine. So then they will not be able to use or abuse the Embeda. So the take-home message is pharmacists are mean. Okay, so they have all these smart techniques to prevent the abuse of the morphine. The next one after morphine is the hydromorphone, and the only difference between the morphine and the hydromorphone is in this position here in the ring. We replaced the OH group with the ketone, and we removed the double bond here. So as we have explained before in the SAR, this will make the ring more flexible, which allows this to interact with the receptor stronger. So then the product becomes more potent, more active. In fact, it is 6 to 10 folds more active than the morphine. And speaking of the number of folds and the comparison between drugs, I just want you to relate or compare between drugs, which one is more active. Don't worry about memorizing, how much is this one more active than the other one. So don't worry about the number of times a drug is more active than the other. Just make sure you are able to compare between them. And just like with the morphine, the side effects of all these opioids would be respiratory, depression, and constipation. The hydromorphone is available in solutions, suppository, tablets, liquids, and extended dosage forms, as in Exalgo. Okay, the immediate dosage form is called Dilaudid. And speaking of brand names, you will need this for the clinical parts, not on my parts. You need to know the brand names, or you could check with the instructor to see if you really need to know all the brand names or certain ones. Anyway, then the last one, or the next one, is the oxymorphone, and the only difference between the oxymorphone and the hydromorphone is the addition of OH here, which increased the activity 2 to 3 times more than the hydromorphone. So it's about 12 times more active than the morphine. And again, it's available in solutions, tablets, extended release form, as in Opana ER. Okay, and we have already discussed these before in the SAR. The next 3 medications, we'll put them together because they have similar properties to the ones we discussed before. These are the codeine, hydrocodone, and oxycodone. So these are the structures, and just like the morphine, hydromorphine, and oxymorphone, they have the same differences in structures between them. The only addition with these 3 is the CH3 here, and here, so which makes them inactive. So all these 3 are prodrugs, so they have to be converted to the OH form to be active, which gives them longer duration of action. It also improves their lipophilicity, and also makes them less active because only 10% of these drugs are converted to the original one, without, the one without the CH3 here. So the same thing applies. So this one here is less this one is more active than that, and this is more active than this. Again, just as a reminder, the enzyme that converts any one of these back to its active form is the CYP2D6, which is an enzyme that varies from one person to another. So inter-individual variability should be an issue. Again, all of them can cause respiratory depression and constipation. There's something unique, or some unique concept I want to add, which is that if you remember in the SAR, we said that the addition of the OH group here at position 4 would prevent these drugs from binding to the cough center. So these two, the oxymorphone and oxycodone, cannot be used as antitussive, while these will have the antitussive activity. In fact, we all know that codeine is one of the products that's used as antitussive drug. The last one in this class of the multi-cyclic mu agonist, full mu agonist, is the levorphanol. In the case of the levorphanol, they remove the OH group here, they remove the double bond, and there's no OH group here, and they also remove the fifth cycle here, so it's tetracycline instead of pentacycline. Now, despite the fact that there's no OH group here, and they remove that, despite the fact it's does not bind as well to the receptor, it's you'd expect that to be less active. But the fact that it's more lipophilic has increased its activity. So overall, its ability to cross the blood-brain barrier is much more than the morphine and the other ones that are more polar. So, and this overrode the the fact that it is less active. So overall, it's 4 to 8-fold more active than the morphine, or has enhanced activity over the morphine. Another unique feature about this one is the fact that it has a long duration of action, so it can be used without having to design an extended release form, which is an advantage, except that excessive abuse can cause the drug to stay longer in the body, build up, and cause some more toxic effects. Okay, the next class we will talk about is the partial mu agonists, and the one example we will use is the buprenorphine. Buprenorphine has a unique feature and unique SAR features. And all these unique features are due to the fact that at this position, at position number 7, we have this isobutyl group, which explains the name, where the name came from, buprenorphine. It has this isobutyl group, and at this carbon here, there's an OH group. So the presence of these groups made the drug very potent. Apparently, this part here is lipophilic. It binds to some lipophilic part, another part of the receptor, making van der Waals interactions or hydrophobic interactions. And this one here also is able to form hydrogen bonds. So it actually binds very strong, with high potency to the mu receptor. In fact, it is like 25 to 40 times more potent than morphine, which is interesting. That although it is more potent, which means it smaller dosages in 2 milligrams um, are enough to replace the morphine. It's much more potent than the morphine, but at the same time, once it binds, it does not give the full effect. It only give you a partial effect, which is due to this cyclopropyl methyl group. So it is not a full agonist. It's a partial agonist. Okay. Um, it's because it's highly bound to the receptor. It's known as a pseudo-irreversible. It has a pseudo-irreversible binding, which means if you remember, those that bind irreversibly to the receptor, they would form hydrogen bonds that would not break, and they will be stuck with the receptor forever. This one does not form a hydrogen bond with the receptor. I'm sorry, I meant covalent bond. So this one does not form covalent bond. So the irreversible drugs normally make covalent bonds with their receptors, and they never leave the receptors. This one does not form covalent bond, but it does form a strong interaction that makes the drug similar to the irreversible type of bindings. And because of that, the drug has a long duration of action. It's only taken once a day, and because of that also it's slowly dissociated from the receptor, therefore the withdrawal effects are much less than the case of the other drugs. So basically, once you stop the drug, it weans itself out, slowly. There's no need to gradually decrease the dose, which is very convenient for the patients. Also, because of the fact that it is a partial agonist, it can be used in treating people who are addicted to opioids. In other words, it could be used to replace the opioids, like morphine, for example, without causing the euphoric effects, because it's a partial agonist. Okay. The only problem with the pseudo-irreversible feature these drugs have is the fact that if you overdose this drug, even though it's hard to get the euphoric effect, but still if some people overdose it, then they will get respiratory depression, which means that you'll have to reverse the effect of this drug, and this becomes very difficult because you will have to give much higher dosages of the antagonists, which we'll talk about soon, such as naloxone. So we'll have to take a lot, tenfold the normal dose of naloxone, to replace the buprenorphine. Okay, so this is one downside. I guess the downside feature for the use of this drug. Also, one of its features is the fact that it is extensively metabolized through the first pass effect if it's taken orally. So this drug is only taken either sublingually or by IV, or there are also the transdermal patch. There's the transdermal patch forms. Finally, if you use the patch, then the patch should be avoided from the hot or from the heat, because this can affect the release of the drug. And I'm going to skip these paragraphs. They're not really important. You can read them by yourself. And then, like we said, this drug is available in the sublingual formulations, IV and patch. So the sublingual formulations, there are two different kinds, taken sublingually, tablets. The first one is the Subutex, which contains only the buprenorphine. It comes in strength 2 and 8 milligrams. And the other one is the Suboxone, which has both the buprenorphine as well as the naloxone, which is an antagonist. And the reason they combine the naloxone antagonist is to prevent people from abusing the buprenorphine. Just in case if someone tries to overdose the buprenorphine, then they get the effect of the naloxone. Okay. These two examples of the other partial mu agonists, multicyclic, I'm gonna skip. Okay, you can read them by yourself if you want to. The next class of opioids are the multicyclic um, GABA agonists, mu antagonists. So they work as agonists on the GABA receptor, but they block the mu receptor, so they are mu antagonists. Although we should really um, distinguish them from the pure mu antagonists. In fact, if we want to be precise, we should call them mu partial antagonists. So the kappa agonists, mu partial antagonists. If you remember the kappa receptor, the activation of that receptor would still give you the analgesia. It will not give you euphoria. It will actually cause dysphoria. It will also cause less respiratory depression. So you get these effects from the kappa agonists. You will have less respiratory effects, less constipation, less euphoria, and of course less potential for addiction. The only side effect is the dysphoria and the diuresis. These are the major, plus the sedation, of course. You should highlight that the fact that these drugs are partial antagonists, not pure antagonists. Let me explain the difference first between the partial antagonist and the pure in this graph. Okay, so this graph here shows on the y coordinates you have the opioid effect. On the x coordinate you have the dose of the drug. So normally with the morphine, as you increase the dose, you get the full effect of the opioid effect, whatever that is, euphoria or analgesic. So you get the 100%. And then with the antagonist, pure antagonist, as we will see, such as the naloxone and the naltrexone, you have zero effect, no change at all to the receptor. Okay, so that's a complete pure block to the mu and in fact all the other opioid receptors. But then you have something in between. Those in between are called partial. You can call them partial agonists or partial antagonists. It won't make a difference really. So I wanted to call this a partial antagonist because this one in orange, because it's closer to the antagonist. And then these in the middle are partial agonists. So we already talked about the buprenorphine partial agonist, we discussed that already. And in the newer class here, the multicyclic kappa agonist, mu antagonists, we're actually talking about the mix of kappa agonists and mu partial antagonists, such as pentazocine and the nalbuphine, and the third example. So there are 3 examples on this. Anyway, so why this is important? Because as you can imagine, if you have a partial antagonist, there is still a little bit of effect that you can get from these partial antagonists. So the question for you is, do you think these drugs can still be abused even though they are classified as mu partial antagonists? Let's find out in the next page. So for now, the effects we see are from combining the advantages of using these kappa agonists are, like we said, we get the analgesia, but we don't get the euphoria. Disadvantages would be getting the dysphoria and the sedation. Again, one of the advantages of using kappa agonists is you have less respiratory depression, less constipation, and less euphoria and less addiction. Okay. So the next example on this class of medication is the butorphanol. again, this is one of a kappa agonist and mu antagonist, or we should say mu partial antagonist, just like the one before. Advantages would be less respiratory depression, less euphoria, etc. It can cause dysphoria or diuresis, um, which is higher than the one before. Um, what's unique about this drug is that, I mean, one feature of this drug is that it goes into a significant first pass metabolism, so it cannot be taken orally. Normally, this medication is taken by IV or actually by nasal spray. Is the brand name for this drug is called Stadol nasal spray, and it's actually a class 4 medication, um, controlled substance of Schedule 4. The same with the pentazocine Schedule 4. The one before, the one we talked about earlier, um, it was actually an RX prescription. Anyway, so this one here is used as nasal spray, and it's useful in moderate to severe pain, and in the case of migraine or dental pain. The last example is the pentazocine, and um, this one, just like the ones before, has the same feature before. Now, because of the fact that these drugs could be um, abused, even though it's a mu partial antagonist, just the fact that it has a little bit of agonist in them. Let me put the graph. So just the fact that the pentazocine, for example, has a little bit of agonist activity, it can still be abused. So that's why um, pentazocine, the brand name for it is Telwine. There's another product for Telwine called Telwine NX, which has the pentazocine plus the naloxone, which is the antagonist. The only which is similar to what we did with the Embeda and the Suboxone. So we added naloxone, and the only thing is here we did not use a pellet or anything. This drug is simply um, naloxone. If the drug is taken orally as it's supposed to, then naloxone will not be absorbed. Only the pentazocine will be absorbed, because naloxone will go through the first pass metabolism and will be damaged. Um, so only the pentazocine will be taken. But if the patient decides to, um, take the pentazocine by IV or a different route, to to get high on the pentazocine, then naloxone will be effective and it will work as an antagonist. There's a question that was asked by one of the students. His name is Ben. It was a very creative question. He was asking if the kappa causes dysphoria, then mu causes euphoria. Why did you combine a kappa with mu, and then they both would cancel each other? It was a very nice idea. This example here shows that this is not the case. Pentazocine is a kappa agonist, and it has a little bit of mu partial agonist or antagonist. So when combining the dysphoric effect of the kappa and the euphoric effect of the pentazocine, even though it's a little bit, um, people can still get the euphoric effect. To explain how this is possible, this is very similar to in the case of drinking alcohol, where you can get the euphoria, but then the next day you get the hangover, anxiety, and the dysphoria, the dysphoric effect. So again, just the fact that one receptor causes dysphoria and the other one causes euphoria, they do not cancel each other. You can still get both effects. Okay. The next class we will talk about is the opioid antagonists. So these are the ones right here. They are pure antagonists. They have no any agonist activity, so they simply block the receptor and they prevent the binding of any opioids. And these are very useful to save life of someone who has overdosed on any of these opioids. Okay, so as you might expect, they should have a higher binding affinity to the receptor, um, than the other opioids, such as morphine, for example. Therefore, it can displace the morphine from its binding site receptor. We have, for example, on these opioid antagonists, these four molecules, um, naloxone, naltrexone, nalmefene, and methylnaltrexone. So the naloxone, if you remember, we said the substitution on the nitrogen if it's in the allyl function group, or if it's in the cyclopropyl methyl, like these, then the drug becomes antagonist. So in this case, the naltrexone have the allyl, the naloxone has the allyl group, naltrexone has this one, and all of them have the cyclopropyl methyl. The methyl naltrexone is the only difference between this and that is the addition of the methyl, as we'll explain very soon why. And then we have the nalmefene, which substituted the O with the carbon and caused increased lipophilicity. So naltrexone, naloxone, naltrexone, this one here is actually the naltrexone is twice as potent as the naloxone, probably or mainly due to the better distribution, to its ability to cross the blood-brain barrier. This one here, when we substitute the oxygen with CH3, with CH2, it becomes more lipophilic, so it's more able to cross the blood-brain barrier. This one here stays positively charged all the time, because the CH3 here does not leave. It's designed to be in a quaternary analog, so it does not cross the blood-brain barrier ever, and it stays in the circulation. It acts locally on the intestine, as we'll see, to prevent or reverse the constipation caused by the opioids. Not necessarily for the people who abuse opioids, but people who actually take these opioids for chronic pain or or cancerous patients. So these forms are available IV. In fact, the methotrexate, the Relistor, is available as a subcutaneous injection. These three are available. These are available IV. There's something unique about the naloxone, Narcan, which is the fact that it's available as nasal spray. So the Narcan is available as nasal spray, and it's actually available at pharmacies. I checked the Texas law, and apparently it's a federal law that says that naloxone or Narcan or even naltrexone can be taken without. Basically, they can be taken as directly from the pharmacist using what's called the standing order. If you're familiar with the standing order, just like the vaccines, for example, if somebody comes to the pharmacy, you want to take a vaccine, then you can use what's called the standing order. So normally pharmacies have a contract with an MD, so that would sign prescription on a standing order for these vaccines, as well as these products, the naloxone, for example. So then the pharmacist can just use that drug, write a prescription for using the standing order, and then dispense the Narcan. And normally the patient does not have to give their name or any of their informations, and they are basically protected if they want to use this medication. They could save the life of a friend or relative. So this one is available as a nasal spray, and these two are IV, and this is subcutaneous. What else? The naltrexone is also available orally. It could be taken, like we see with the other medications, where it's combined to prevent the agonist effect of the opioids. So it can be taken orally. This cannot be taken orally. It's available. It has to be absorbed either IV. It has to be given IV or nasal spray, or it can also be given sublingual, as the case with the Suboxone. The naloxone was combined with the buprenorphine, like the Suboxone. What else? Nalmefene has a long duration of action. I think this covers everything. I have some pictures to show about the Narcan just to give you an idea how it looks like. Okay, so again, the Narcan or naloxone is available as a nasal spray, a syringe, and if somebody has taken overdose of the opioid, then the naloxone, which has a higher affinity to the opioid receptor, will displace the opioid, uh, that morphine, for example, or opioid from the opioid receptor, and then reverse the effect of that opioid. So would reverse the respiratory depression and save the life of that patient. And also, of course, in this case, you will see withdrawal symptoms, but um, you know, it wouldn't matter in this case because saving the life would be more important. And like I said, whoever use these drugs will be to save a life of someone will be legally not liable to any consequences as long as they use this in a good intention. Okay. And the methyl naltrexone is just like the naltrexone, except they added a methyl group here. Now, this methyl makes the molecule positively charged 100% of the time. Now, you might wonder, these are also positively charged, so how come these three can cross the blood-brain barrier, but this one does not? Well, these are positively charged, but through the proton, the hydrogen. So this proton can leave and bind in an equilibrium. So 50%, I mean, just roughly, let's say 50% of the time, these three molecules are unionized, and the other 50% of the time they are ionized. So that portion of the molecule that is unionized will be able to cross the blood-brain barrier and bind to the opioid receptors and reverse the respiratory depression. Okay. They can also bind to the opioid receptor in the intestine and prevent the constipation that is caused by the opioid. The methyl naltrexone would only work locally because on the intestine they are not gonna cross the blood-brain barrier because the CH3 is attached to this nitrogen 100% of the time, so it's always ionized, and therefore it's mainly used to reverse the constipation that's caused by the use of the opioids. Okay, so Relistor was approved for that purpose. It's a subcutaneous injection, and it helps patients who take opioids for chronic pain. Those who continuously take opioids, they will suffer from constipation, so then this could solve the problem. Okay. The next class of opioids are the flexible mu agonists. We call them flexible because, as you can see, they're not restricted by the ring system, the penta or the tetra or even the tricyclic ring. These can freely move, so they're more flexible. And the first example of these are the mipridine, and it actually has 1/10 the activity of morphine, and it has a poor oral availability. It was once among the most widely used opioid analgesics, but it actually has fallen of favor due to the presence of other better opioid drugs. Okay, the rest you could really skip or just read for your own. The second example on the flexible mu opioid agonists is the fentanyl. Fentanyl is actually the most potent opioid among all the ones we have seen. To help you remember that it is the most potent, if you ever seen the fentanyl patches, it actually comes in microgram. So the amount that's released from these patches is in microgram. So it's like 50 to 100 fold more potent than the morphine. Okay. and that's probably due to their high lipophilicity, so they're able to cross the blood-brain barrier really easily, quickly. And then but they are extensively metabolized if they're ever taken orally, so they cannot be taken orally, and that's why they are formulated in a transmucosal, transdermal, nasal spray. Um, of course, the transdermal, like this one here, the fentanyl or the brand name Duragesic, in 12, 25, 50, 75, 100. And then it also comes in many other forms, such as the lozenges, um, the buccal film, and so the Fintora, for example, is buccal. And then you also have the effervescent buccal tablets, um, and there's also a sublingual, um, which is this one here, sublingual, the Abstral sublingual tablet. And then, like I said, it's extensively metabolized by the alkylation, so it always has to be taken through the other routes. Okay, either IV or nasal spray or transdermal, sublingual, buccal, um, all these forms. These three examples we're gonna skip. You can read them on your own, and let's move to the next example. The next example on the flexible opioid agonist is methadone. Methadone, this is the structure of methadone. As you can see, it's more flexible than the other ones with more than one cycle. Methadone has two unique features. The first one is the fact that it has a long duration of action. It has a long T half-life. The half-life is between 15 to 60, and the reason for this long half-life is because the metabolites of the morphine, the methadone. Okay, these metabolites. So this is the methadone. The metabolites for methadones are actually active. So when it is metabolized in the liver, it's converted into these active forms, and so the duration of action continues. Okay, so let's go through this metabolism reaction. So the methadone can go into either dealkylation or reduction at the oxygen here. If it's dealkylated, then by removing methyl, we add the term nor, so it's nor-methadone. Anytime we remove a methyl from a group, from a drug or a molecule, you can name it nor, referring to the removal of the methyl. So it is nor-methadone because one is removed. Now, if you remove the second one, it's called dinormethadone. Okay, both are active, and then if you actually reduce the C double bond over here, you get this OH group, so now it's called methadol. And then again, if you remove one methyl group, it becomes nor-methadol and then dinormethadol. And the circle we can reach this product also through this route. All of them are active forms, which causes the drug to stay long into the body. So in some cases where they use the methadone to help with stopping drug addicts, basically to recover addiction, the methadone long duration of action can be advantageous, because then when you stop the methadone, the drug long duration of action will let the drug gradually be reduced. Okay, although this use of methadone for drug addiction is restricted to only licensed clinicians. Okay, so they should be licensed, federal and state licensed. The second feature of the methadone is the fact that one of these products, the one that's basically the nor-methadone and the dinormethadone, can form this cyclization and produce two different products, the EDDP and EDMP, which are also stay in the body for a long time. They have a long duration of action from 40 to 48 hours. But the problem with these two is the fact that they actually can inhibit the enzyme called CYP2C19. So you want to pay attention that sometimes it's not just the drug that can inhibit the metabolic enzymes. Sometimes the metabolites of a drug can inhibit some other enzymes, in this case the CYP2C19. So that's all about I want you to focus on. The next example, or the next class, are those that has dual action or dual mechanism of action opioids. So these are the ones that can not only stimulate the mu receptor, but they actually inhibit the reuptake of norepinephrine or the serotonin. 5-HT stands for serotonin. So these would inhibit the breakdown or the reuptake of norepinephrine or serotonin, such that they stay longer near to their receptors. And then it was found that this would reduce the pain of you know nociceptive pain. So by combining these two mechanisms, we could rely on the reuptake inhibitors and reduce the amount of opioid drugs, and therefore we could avoid the problems of the respiratory depression, constipation, sedation, tolerance, dependence, addictive ability of all these opioid drugs. The example of a dual action is tramadol. It has actually 2 chiral centers, and therefore you can imagine that there are 4 different enantiomers, racemic mixtures, and then some of them they inhibit the reuptake of the norepinephrines, others inhibit the reuptake of the 5-hydroxytryptophan or serotonin, and the other one also can actually stimulate the mu opioid receptor, and its metabolite, the metabolite of that last one, the dextrorototorazomer, is also active. It can stimulate the mu opioid receptor. It's 6-fold more potent than the previous one. And the last class of drugs we'll talk about in this chapter are the opioid-based anti-diarrhea. So, as we have seen, the major side effect for these opioids is constipation. And we also have seen that if we design opioid antagonists, we could reverse that constipation. What if someone have diarrhea? Then we could use that side effect to our advantage, and then we could use these opioids to stop the diarrhea. Okay, so it's basically taking advantage of a side effect and use it as a therapeutic effect. Another example of this idea was the use of antihistamine. The first generation antihistamine, they had a side effect, which is it causes sedation, and therefore that same antihistamine was marketed and as drugs to help people sleep. Okay, well, despite the fact that it causes next day residual symptoms, so it's not recommended that we use these for a long time. But anyway, so examples on these are, we have 3 examples: the diphenoxylate, diphenoxine, and loperamide. In the case of the diphenoxine, it actually is has a Zwitter ion, which means it does not cross the blood-brain barrier. It does not reach the CNS. So you cannot actually abuse this medication if you take it, even though it's an opioid agonist, but it does not stimulate reach the CNS unless it's given at higher dosages. The diphenoxylate, it does cross the blood-brain barrier, so you should be cautious In fact, in both of these cases, we should be cautious, and to avoid any abuse of these two medications. Normally, they are combined. Actually, they're always combined with atropine. So both of these two drugs are available in combination with atropine, and the reason is if someone try to abuse these two medications, then you will get the horrible side effects of the atropine, which is an anticholinergic, and then you also get this heart valve, heart tachycardia that scares the patients or the addict away. So just another mean way that pharmacists do to stop the abuse of these medications. Now, loperamide Imodium, we have talked about this in the past, if you remember. This drug is lipophilic. In theory, you would expect it can cross the blood-brain barrier. It does, in fact, but there is a pump called the PGP pump that would kick it out anytime it crosses the blood-brain barrier cells. This pump would take it back away. Okay, and this pump is also present in the intestine, so it prevents the absorption in the first place before the drug reaches the circulation. But again, a higher dosage of that drug can overcome this pump. It would saturate that pump, but would be really it's going to be a lot of I guess increase in the dosage to overcome that pump. So just keep in mind these opioid agonists are used to treat diarrhea as anti-diarrheal. Okay, and we also have seen the opioid antagonists that are used to treat the constipation caused by, or to reverse the constipation caused by opioids. Okay, so try to put these two together and compare the mechanism of each.